Hello everyone, this is the first lesson recording for day 5 and we're going to be tackling 9.5 polar form of a complex number. So if you recall standard form of complex number, can you give me an example of a complex number? It could be something like 2 plus 3i, right? Or it could be something like negative 3 plus minus 4i. Okay, they are all complex numbers. And what is true about this is that it is going to be in the form of a plus bi. So with complex numbers, you're always going to have a real portion. This is a, is the numbers like this, 2 and negative 3. This is going to be my real part. And the bi tells me the imaginary part. Okay, so in the complex number system, these are examples of complex numbers. Okay, what about a number like 2? Is this a complex number in the complex number system? Yes, it is, because this is same as 2 plus 0i. The imaginary part just happens to be 0. Okay, what about if I just have negative 3i? Is this a complex number? Yes, it is a complex number with the real part being 0 and the imaginary part is negative 3i, or 0 minus negative 3i. Okay, alright, so that's the first thing, is we know the standard form of complex number always comes in this form of a plus bi, where you have the real part and imaginary part. Now, can we graph this? Well, to do this, we can have our standard axis. So to graph this value here, okay, let's start with our example, 2 plus 3i. What we can do is we can have two different axes. Instead of calling it x-axis and y-axis, we're going to call the horizontal axis the real axis. And the vertical axis, we're going to call that the imaginary axis. Okay, so that means the real axis is going to just give us the standard 1, 2, 3, 4, and so on. So negative 1, negative 2, negative 3, and negative 4. But the imaginary axis, I can label the values on the axis as 1i, or I, 2i, 3i, and 4i. And as you can imagine, the other direction is negative 1i, negative I, negative 2i, negative 3i, and so on and so forth. Okay? Alright, so now let's see if you can plot these values. 2 plus 3i. So the real part is 2, so we go along 2 on the real axis, and the imaginary part is 3i, positive 3i. So this is going to be my 2 plus 3i. This is going to be my complex number. 2 plus 3i. It can be graphed in this complex plane, and we call this the complex plane. It's not real plane because we are dealing with real number and imaginary number, real part of the complex number and imaginary part of the complex number. Alright, so let's try to plot the other points. Negative 3 minus 4i, that means the real portion is negative 3 and the imaginary portion is negative 4i. So negative 4i will be right here. So negative 3 minus 4i will be right this point. 2 just has the real portion only. So that means this is my 2. The imaginary portion is 0. So that's my 2. Similarly, negative 3i can be represented right here. And something else. we say that this is a standard form of complex number, but we also can call this the rectangular form. And you can see why later on, because we're going to be talking about polar form of the complex numbers. Okay, so again, any complex number can be graphed like a point as a comma bi, right? Where a is the real portion, bi is the imaginary portion. Okay, now we're going to talk about absolute value of a complex number in standard form. Okay, so let's just recall what do we mean by absolute value. Well, we know the absolute value of, say, 8 is going positive 8 is just 8. And we also know that absolute value of -5 is going to be 5. Do you remember some other definition of absolute value? Some of you might remember the absolute value of a number is the distance from the 0. So if I was to put that 8 right there and 0 here, what it's saying is what is the distance from 8 to 0? That's going to be 8 here, right? So distance was 8, right? You don't have to write this. That's why I'm doing it on color paper. Oh, same thing here. If I was to think about -5, what is the -5 here? What is the distance? It is from the 0. It's just this distance here. And the distance is equal to 5. So that is the reason we said the absolute value of -5 is equal to 5. So when we are talking about absolute value of a complex number, it's really talking about the distance from 0. Okay? So if I have a generic point, a plus bi, a generic complex number here, I can plot it in the complex plane as a plus bi. And so to be able to make the generalization, let's just let this complex number be a plus bi. Okay, so this z is referring to a complex number. Okay, and if I look at this coordinate here, what is my horizontal distance? Is going to be this, is going to be a, right? And this is going to be b, because we are forming a right triangle. And so how do we figure out the distance the complex number is from 0, or the origin? Okay, so, and that is going to be the radius, or that is going to be the absolute value of z here. Okay, so, and how do I find that this distance? That is just using the Pythagorean theorem. A squared plus b squared is this distance squared. So this comes from here. You can say that z, absolute value of z, or the complex number, is going to be square root of a squared plus b squared. So whatever a value is, whatever b value is, you're squaring each of them and then adding them and taking the square root of it. So that is the formula for the absolute value of a complex number. So let's try to do some examples with that formula. Okay, so if example, find absolute value of z if z is defined as -2 plus 4i. Okay, so it's a complex number that has a value of -2 plus 4i. So then how do we figure out absolute value of z, absolute value of this complex number? Well, absolute value of z is going to be a squared plus b squared square root of that. So a squared plus b squared. What is a? A is -2 whole squared. What is b? That's 4 whole squared, and take a square root of it. And that's going to be positive 4 plus 16, square root of that. And that's going to be 20, which simplifies to what? Okay, so radicals. I can break that up as perfect square of square root of 4 perfect square of 5. So that simplifies to 2 root 5. So I can say that absolute value of this complex number is 2 root 5, or the distance from 0 of this complex number is 2 root 5. Now let's extend the idea of the complex number in complex plane to polar plane. Okay, so to do that, let's consider a complex number 3 plus 4i. 3 plus 4i, if I was to talk about 3 plus 4i, that means in the real axis, the value is 3, and the imaginary axis will be 4i, so it will be right there. Okay, all right, so then if I was to draw a triangle, I know that this is going to have the value of 4, and this is going to have the value of 3, or A and B here. Okay, and if I was to draw a radius here, or if I was to draw a line from the origin, directly from the point to the origin, that is going to be my measure of theta, and the radius would be represented by the distance, the absolute value of the complex number we just found. Okay, so now let's do some calculation to figure out what r value is and what theta is in this case. So for 3 plus 4i, r is going to be equal to, well, 3 squared plus 4 squared is going to be r squared. So it's going to be the square root of 3 squared plus 4 squared. Or you can also say it's the absolute value of the complex number there, right? And that is going to be 5. Okay, and what about theta? Well, I know that tangent of theta is opposite over adjacent. So tangent of theta is 4 over 3. So, or theta is inverse tangent of 4 over 3, which is approximately 53.1 degrees if you use a calculator. Now, if I was to have it at more generalized, say if I have a plus bi as my complex number, then r is just going to be square root of a squared plus b squared. Okay, which is same as the absolute value of this complex number. So that is something that's going to be helpful. Now let's talk about the complex plane, polar plane. Okay, so polar form of complex number is the same number. Okay, so here we're really dealing with same number here, but we're really, this is 3 plus 4i, but we're really trying to plot it on the polar plane. Okay, so what that means is, let's just draw some circular lines around the polar plane. So this is when radius of 1, we are creating a polar grid. So to consider the polar plane, we just need to consider what A represents and what B represents. A, well, we know that A over radius, or r, is going to be sine of theta. So we can say that sine of theta is going to be equal to A over r, or we can represent that as A is equal to r times sine of theta, right? And similarly, we can do the same thing with B. B is going, well, cosine of theta is going to be B over r. So then from here, we can say that B is going to be equal to r times cosine of theta. So what used to be the A plus BI, we can write, this is A plus BI. This used to be my standard form. This is my standard form. Okay, I'll continue in the next video.